This presentation will resume the major points of the work entitled Prediction of Fatigue Crack Growth using a Damage Model. Fatigue crack growth prediction is a complex and really important field of study. Since the 70s, the ADA and ΔK approach has ruled. However, this approach is not able to predict the effect of stress ratio and variable amplitude loading on the propagation of cracks. In fact, the great success of K has obscured the fundamental aspects of fatigue crack growth and its understanding. The true way to understand it has to be related to the mechanisms acting at the crack tip. The plastic deformation at the crack tip is well accepted to be the main mechanism behind fatigue crack growth. Damage is an entity directly connected to the occurrence of plastic strains. Thus, at the crack tip, where plastic deformation is important, damage has to be accumulated by the material due to the activation of the mechanisms of nucleation, growth, and coalescence of microvoids. This study pretends to access the influence of the introduction of the GTN damage model in a previous developed node-release numeric model used to predict FCG. The considered numerical model predicted FCG took the release of nodes each time plastic strain reached the critical value. The material isotropic elastic behavior is modeled through Hooke's law. The yield surface is given by von Mises yield criterion, and the hardening of the material is predicted through The isotropic and kinematic hardening parameters were simultaneously calibrated using the stress-strain curves obtained in smooth specimens of the experimental low-cycle fatigue tests. Parameters for the Gerson-Tvegaard and Needleman, as known as GTN damage model, are shown in this slide, together with elastic properties and parameters for the hardening loss and the yield criterion. The study was performed under plane strain conditions in compact tension specimens. The mesh considers three distinct zones: a very refined area near the crack tip to better approach the stress at this zone, a transition area, and a cursor mesh zone, far away from the crack tip, to optimize computation times. At the end, 7,287 isoparametric elements are used. This slide presents the DAD and delta K curves for both models, with and without GTN, natural, and log-log scales. It was expected that the fragilization induced by the GTN damage model would result in an increase in the fatty crack growth rate, particularly for higher values of delta K. However, as can be seen in both graphs, for lower values of delta K, the GTN induces a protective behavior. At some point, this trend is reverted and the faster propagation is achieved with GTN, as it was expected. In log-log scales, without GTN, the DADL curve has an approximately linear behavior. With GTN, this trend is also followed, but only until the protection given by the damage model is reverted in a faster propagation. explain the strange protective behavior induced by the damage model for lower values of delta K, the plastic strain was studied on the node located at the crack tip for two distinct initial crack lengths. Please note that higher initial crack lengths result in higher delta K values when the stable propagation zone is reached. For the first initial length, equal to 11.5 mm, the numerical model considering GTN predicts a slower propagation rate. On the other hand, for the second initial length, equal to 21.5 mm, the numerical model considering GTN predicts a faster propagation rate. Thus, we can say that the inversion point on the influence of the damage model occurs between these two values. In this slide, the plastic strain evolution is presented for both models for each initial crack length. The plastic strain is a cumulative entity, and it is presented here for an entire propagation. To assure that the results are comparable, the same propagations were studied in both models, corresponding to the stable propagation zone. For both initial lengths, the plastic strain is higher at the beginning of the new propagation in the model considering GTN. The results show that for 11.5 mm, the plastic strain increases faster without GTN, and that for 21.5 mm, this trend is reversed. These results explain the obtained ADN delta K curves. However, the results themselves required an explanation. The plastic strain was also analyzed in the Westwood cycle before each propagation presented in the previous slide. Results show that the previously described trend is followed. For 11.5 mm, the increase in plastic strain is much faster without GTN. Thus, when maximum force is reached, the initial difference in plastic strain has already significantly decreased. Moreover, on the unloading phase of the cycle, the trend is repeated and the difference in plastic strain keeps to decrease. At the end of the cycle, the curve of the model with GTN suffers a kind of planing, being this behavior associated with the occurrence of crack closure. For 21.5 mm, the plastic strain increases faster with GTN. Note that the difference at the beginning of the Westwood cycle between both models is smaller for this initial crack length. The planing effect on the curve The next step was to analyze the crack tip open displacement on the node immediately behind the crack tip. This analysis was performed for both models and for each initial crack length. This slide presents the CTOD results on the same cycles referred on the previous slide. The results show that for the model without GTN, the crack is always open on the last cycle before propagation. There is no crack closure. On the other hand, the model with GTN points significant crack closure for 11.5 mm. On the other initial crack length, the crack closure is small, as the crack is almost always open. Thus, it is to expect that the higher level of plastic strain induced by the GTN model results in higher plastic weights and consequentially higher levels of crack closure. Crack closure was analyzed during two entire propagations, the same ones discussed previously. Note that a crack closure level of 20% means that the crack is closed for 20% of the whole cycle. The results are in accordance with the ones referred on the previous slide. For 11.5 mm, the crack closure suffers an initial peak and stabilizes at about 20% for the model with GTN. Without GTN, the same trend is followed. However, the crack closures tend to disappear. For 21.5 mm, there is an initial peak in both models and then a reduction in crack closure. This phenomenon is related with strain wasting. Note that this reduction is more important in the model without GTN. Die-air crack closure for 11.5 mm protects the material, reducing the plastic strain accumulation and therefore resulting in a lower DADN. On the other hand, as the crack closure ceases for 21.5 mm, the fragilization induced by the damaged model results in a faster buildup of plastic strain and consequentially in a higher DADN. To prove the importance of crack closure on the crack propagation rate, this phenomenon was disabled on the model considering GTN. This was achieved by removing the contact between the two crack flanks on the numerical model. Note that the initial plastic strain, both at the beginning of a new propagation and at the entrance of the load cycle, is alike with and without crack closure. However, as previously pointed, as the protection induced by crack closure ceases, the accumulation of plastic strain is much faster. This results in a significantly different DADN delta K points for 11.5 mm. For 21.5 mm, as the crack closure ends up ceasing due to strain lasting, the effect of crack closure is less important, and both points are almost overlapped. This study allows us to conclude that the introduction of the GTN damage model on the previous node-release numerical model results in a tendency of the plastic strain to slide to higher levels. However, these higher levels of plastic strain result in higher plastic weights and more plastic-induced crack closure, which protects the material, reverting the fragilization trend induced by the GTN. When crack closure ceases for high values of delta K, the harsher plastic strain levels result in the expected higher propagation rates. Thus, the crack closure is a fundamental crack tip mechanism leveling the DADN behavior of the models with and without GTN. Thank you for your attention.